Morning, everyone. I hope that you guys are having a good start to your day. I wanted to let you know a couple of things right from the get-go. There will not be any poll questions today. We have an exam on Wednesday. Our exam will be administered on Canvas. You'll have to log in through Proctorio. You do not have to log into Zoom. If you elect to log into Zoom, I'll be here. I'll be ready to answer any questions or help troubleshoot if anything comes up. Um, then in addition to that, maybe not most important, but very important thing is I will get your exam grades back well in advance of how I did last time. Last time was pretty bad, and I don't want to do that again. And I'm sure nobody wants me to do that again and take forever to grade the exams. Um, so I will make sure that I get them back to you as soon as possible. Oh, just got a series of questions. Give me a second. I had a couple of questions about the exam, practice exam, and won't be able to ask during office hours. I understand. Will we have a periodic table with the polarities of the atoms? Yes, your exam will have a periodic table. It will also have that table that we've seen before that shows the approximate electronegativities. Um, so I will give you those values. The ones that we've seen before, where it's just a select number of atoms, you'll be given those. And more importantly, you'll be given the ones that you need. Second, could you re-explain having Roman numerals in a chemical formula? We went over it briefly once, and I want to feel confident about it. Totally. I'll do that before I go to anything else. Now, um, next up. So let me get. Okay, so anytime you ever see, and I'm getting a series of messages. Scratch paper. Do you want us to use scratch paper or we use our iPad? Scratch paper. No iPads. Will we get a note card? Yeah, just like your previous exam, you can use note card. Okay, so the question was about Roman numerals. If you ever saw iron, IV, well, that IV stands for 4. If you ever saw, let's say, copper, 2, well, that stands for 2. Now, a really good and a fair question here is, hey, you didn't denote positive or negative. Well, as kind of a learning objective or thing to think about, iron and copper, and I'll go down to the next slide because that actually has the periodic table on it. Could anyone add to the chat what types of elements are these? You'd classify those as being on the left-hand side of the periodic table. We've got copper right here, and then we've got iron just to the left of it. So they're both metals. They're transition metals, more specifically. I like that answer. Great job. Great job, Jaden. But these are metals. And whenever it comes to metals, what do they love to do? Metals love to give up electrons. And when they give up electrons, they form what are known as cations, C-A-T-I-O-N-S. So those are positively charged ions. So anytime you see iron 4 like that, what you really mean is iron 4 plus. Same thing for copper. Well, copper 2. Copper is a metal. It's going to be a 2 plus ion. Now, I'm sure there's somebody out there who's thinking, well, will I ever see a non-metal? Will I ever see carbon 3? And the answer to that question is no. That does not and cannot exist. So when it comes to Roman numerals are unique in that they are for, I'll say, reserved for positively charged ions. I'll say slash cations. Sorry, I just got a message on my phone. Okay, so that's the Roman numerals. I hope that was clear. Do we need to learn the properties of the groups of the periodic table? We had to learn their names and sections independently on the last exam. No. Okay, so I think that those are all those questions. For the person who sent me that private message with all those questions, can you confirm as a private message, did I answer all your questions? And if not, please follow up. Scratch paper, do you want us to use paper or iPad? Paper, 100%. No iPad or no additional electronic devices. Good morning, Professor. I can't seem to log into my Texas State account to connect to Zoom. I think I'm under my personal account. I will continue. It seems like if you joined, then you are good. Um, so if you've joined the Zoom, then you are using your authenticated Texas State account. Will we still get a note card? Yes, you can still use a note card. Will the exams be instantly graded after we take it, like how the Canvas thing has an answer key and it's graded immediately? Nope, because I go back and look at the answer key. So I will get them to you as soon as possible, though. For the exam, are we allowed to have a calculator? Yes, you will, but there's also the calculator that is on the accessible through Proctorio. So you really won't need a calculator. Just because the math that we're doing is fairly straightforward. It's like 4 minus 2, 4 minus 2.5. So if you want to use a calculator, you don't need like a graphing calculator. But if you want to use a calculator, go ahead. What was it that you previously mentioned about Proctorio for the exam? Um, we will be taking the exam exclusively through Proctorio. You do not have to log into Zoom. I will be on our regular Zoom call, though, if you want to join and have any questions. Not, let me rephrase that. If you need to join to ask me any questions. So I'll be there for troubleshooting or to just clarify anything that surfaces, in which case then I would, have my phone or something ready to go. Do we need to log into Zoom with a second device? Never mind. Yeah. Okay, cool. So with that in mind, the stuff that we're going to go over today will not be on the exam on Wednesday. This stuff is chapter number 5, and this is going to be, it's going to bridge us from before spring break to after spring break, because if you remember, we've got class today, we've got our exam on Wednesday, and then Monday and Wednesday of next week, then spring break. Hey, Professor, my apartment is literally okay. If your apartment is flooding, it seems to me that you've got a higher priority. So I would take care of that. Get stuff, what or get everything out. Contact the main office and let them know. So don't worry about it. Okay, so and I did mention this earlier, and I'm going to mention it again. There are not any poll questions today, so don't worry about missing them. So everyone's going to get credit for their Zoom participation by being here today. Okay, so we got 95 people. I kind of expected that after I said that, and we dropped to like 55, but we're still at 95 right now. Just because I know, oh, this isn't going to be on the test, and we don't have to answer poll questions. Okay. Um, at any rate, it's being recorded, just like always, and let's go ahead and get cracking. So we are moving on to chapter number 5. Now, chapter number 5 is kind of a dense and bulky chapter because we're talking about chemical equations. Another way of phrasing that is chemical reactions, because whenever you look at a chemical equation, what that's explaining is a chemical reaction. Now, we've looked at the periodic table, and this is kind of the bulk of the periodic table that we are most interested in. If you remember, there are things underneath, like there's the two kind of sections down at the bottom. That's the lanthanides and actinides. We don't really talk about those. We talked about those when we talked about our electron configuration, but that's about it. Now, when you look at this and you look at the periodic table, one thing that I think everyone kind of always makes this observation is that whenever we explain metals versus non-metals, I got a private message. Correct. We do not need a second device on Zoom. The exam is just on Proctorio. Okay, so we've got metals versus non-metals versus metalloids, which actually somebody asked me earlier if you'd have to know about properties of different substances. And I do need you to know about metals, nonmetals, and metalloids. So metals are great at conducting heat, electricity. They also have physical properties like they're shiny, they're hard, and they're going to be solids at room temperature. Nonmetals, by comparison, usually they're not good conductors of heat. So I'm going to say bad heat. Actually, you know what? They're not good at conducting heat or electricity. So I'm going to say they are poor conductors. You would not want them driving a train. So they're poor conductors of electricity and heat. And typically at room temperature, they're not solids. And if they are solids at room temperature, if they are, they're very brittle. And not a single person gave me a pity laugh at my train joke. I understand it wasn't very good. Metalloids, by comparison, well, they are good conductors. And actually, I'm going to go ahead and qualify that and say they can, thank you, can be good conductors. For example, um, they can be like silicon, for instance. Silicon as a metalloid can be a good conductor of electricity, but not necessarily heat, which is really great for semiconductors. I'll say semiconductors and microchips. So that's why it's good whenever you pick up your phone and it doesn't burn your hand because it's conducting a lot of electricity, but it's not conducting a lot of heat. Whereas if you had nothing but copper or gold wiring in your phone, that would be conducting heat and electricity, in which case you probably have to carefully hold your phone. Okay. But where I started with this is one of the big observations that people typically make is they look at the periodic table and they're like, man, the left-hand side here, which I've kind of poorly circled in blue, it's a lot of metals. And yeah, you've got this group in the middle, your TMs, your transition metals, but they look at it and they say most of the elements in the periodic table, they're metals. You're absolutely right. So that's not really I mean, that's sort of an observation and a conclusion that lots of folks come to, and that's an accurate conclusion. Now, when it comes to what do most chemists study, maybe not most, but what do lots of chemists study? They study these. These are commonly known as your main group elements. Main group. These main group elements, you're going to see time and time again that, we're carbon-based life forms. So we're concerned with carbon, a main group element. We're concerned with how carbon reacts and how carbon bonds with everything else. Now, I want to highlight a couple of these other elements, specifically hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. One of the reasons for this is that these different elements, what they have a tendency to do and what they kind of prefer to do that makes them very unique is they form what are known as diatomic gases. So if you were to ever go to go to a hospital or go to a place where someone's receiving some sort of assistance with breathing or something like that. Sorry, let me rephrase that. If you were to ever see someone who has an oxygen tank, they have this right here. Oxygen as an O2, or sorry, oxygen as O2, a diatomic gas. Now, that's significant because these elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, they prefer that state. That's their base state. They are diatomic gases. Now, we've talked about things like CH4. That's hydrogen. Absolutely. Hydrogen can bond with other things. Fluorine, nitrogen, oxygen, chlorine, bromine, and iodine love to bond with other things. But they are what they are going to default to is they are going to be diatomic gases. Now, that is a comparison to these guys, your noble gases. So diatomic gases, I say diatomic gases versus your noble gases. Now, let's just imagine, and I'm going to draw a beaker. Let's say you had a beaker that had a lid on it. It's closed off, so nothing can get in there for a diatomic gas and a noble gas. Let's say that this was filled with uh, O2, oxygen. If someone said, oh, this has oxygen gas in it, well, what you have in there is a bunch of O2 molecules. There's one. Here's another. Here's another. You have a bunch of oxygen gas molecules floating around in there, thousands of them. Now, if you were told, hey, I've got helium gas. Well, helium as a noble gas, what do we know about noble gases? I'm looking for a word. It starts with an S. If anyone could add, read my mind and add to the chat the word that I'm thinking of that starts with an S. Stable. Perfect. Noble gases are stable. Now, that's something that's like, okay, cool. Yeah, I get it. I understand the word stable. But how do we apply that in comparison to O2? Well, O2 is stable. That is stable. But how does it reach that stability? By having two oxygens. Okay, so this right here, I'm going to get the highlighter tool actually. That is stable. That is stable. That is stable. If you said, oh, I'm going to put oxygen in there and you just got one single oxygen atom in there, give me a Y or N if this individual oxygen atom is going to be stable when you add it to there. No, it's not going to be stable. So as an individual oxygen atom, oxygen's not happy. It is not stable. Okay. For those of you who answered Y or N, I hope that makes a little bit of sense. And I hope that this makes a little bit of sense as well. Helium gas, for instance, or Ne gas, for example. If you added helium or neon to this beaker, it would just be Ne, Ne, Ne. Now, let me ask you this and give me a 1 if yes, and give me a 3 if no. Did I draw any bonds between these neon atoms? No, I didn't. And that was intentional. There are no bonds between these neon atoms. So this is stable. This is stable. This is stable. My point is that neon does not need to bond with anything else in order to be stable. Does that make some sense? Give me a Y or N in the chat. Okay. So the point of this explanation and the point of what we've just talked about is I want you guys to feel comfortable with the idea that different atoms or different, let me say, different elements. Okay. I got a private message. They have strong covalent bonds, double bonds, the O2. That's why they're stable. That's a fantastic question that I got as a private message. The O2 molecules, they have the strong double bond that holds them together, and that is how they are stable. If we think about this in terms of, let's go, I'm going to go up to the previous slide because I want to draw a Lewis dot structure of O2. And then I'm going to draw a Lewis dot structure of neon. Okay, so Let's imagine that both of these atoms, what's the rule that atoms or elements want to follow? I'll give you a hint. The octet rule. Every atom, with a couple of exceptions, basically every atom wants to have 8 electrons around it. So if I were to draw a Lewis structure of neon or any of my noble gases, yeah, they'd want to have full electron cell. So neon would look something like this. Can you give me a 9 in the chat if you're good with that model for neon? Okay. Now, oxygen. If I drew a single oxygen atom, oxygen has 6 electrons surrounding it. So it would look something like this. 6 electrons does not have a complete octet. Give me a 5 in the chat if you follow. Okay, yeah, I see oxygen doesn't have a complete octet. So without a complete octet, this is stable. This is therefore unstable. Now, that's why this rascal right here wants to share electrons. Now, this is rolling in with 6 electrons. Let's think about our process for drawing a Lewis structure of a molecule. We have to come up with the total number of electrons, total number of valence electrons. If we have 2 oxygen atoms, we have 12 valence electrons to draw. So I'm going to draw my 2 oxygen atoms. I've drawn 4. Now, if I complete the octet of each one of these, okay, now I'm going to highlight. Got 2, 4, 6, 8, 10, 12, 14. I've drawn too many electrons. So that structure doesn't work. So I'm going to erase these. Now what I'm going to do is I'm going to erase a pair of electrons and a pair of electrons. I'm going to erase 4 electrons to add back 2. So now, before I proceed, could everyone give me a 0 if they are on the same page as me and they're following what I'm doing? All right, great. So now let's go ahead and highlight and count up our electrons. 2, 4, 6, 8, 10, 12. Okay, there's our 12 electrons. We had 12 electrons to draw. That's what we got. By satisfying the octet of each one of these atoms, we made it stable. Neon, 2, 4, 6, 8. We didn't have to do that. Neon, argon, krypton, xenon, and so on. We don't have to do that. Whereas the rest of these rascals, they achieve that with either a single or a double bond. If we're to look at fluorine as a diatom, is what it's known as, fluorine rolls in with 7 valence electrons, times 2 gives us 14 valence electrons total. I've kind of jumped a little bit. I've got my central structure of F. So I've drawn 2 electrons. I've got 12 more electrons to draw. Could everyone give me a 3 in the chat if they are good with what I've got so far for fluorine as F2? Okay. So now let's just go ahead and complete the octet. Boom, 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 boom. Now let's count up our electrons. What I'm counting for is I want to see 14. So 2, 4, 6, 8, 10, 12, 14. 14 electrons. F2 has a single bond. Okay. So could everyone give me a 6 in the chat if they recognize that fluorine has a single bond? Oxygen has a double bond. Give me a 6 in the chat if you see that. Now, after that, my follow-up question to all of this is, could anyone venture a guess what type of bond is N2 going to have, do you think? Based on maybe a trend here. Single bond, double bond. What do you think N2? John, I love it. Perfect. It's going to have a triple bond. Now let's go through that process of drawing that out. How many valence electrons does nitrogen roll in with? We got Tesla, great. It's going to have five. So five valence electrons. There's two nitrogens, so five times two gives us 10. Again, I always kind of prefer to draw the electrons out so then I can kind of undo my work. 2, 4, 6, 8, 10, 12, 14. 14 electrons. I only had 10 to draw, so I need to erase. And whenever I'm adding a double or a second bond, I'm erasing 4 electrons to add 2. So here's 2, 4. I'm going to add a double bond. Okay. Now let's count it up again. 2, 4, 6, 8, 10, 12. Still too many. Erased all those. Now I'm going to get rid of 2, 4 so that I can add that right there. And that's how I get to nitrogen having a triple bond, or N2 having a triple bond. All right. So these are unique elements in the way that they like to kind of arrange themselves and their sort of preference, their natural inclination. Um, and so these are diatomic elements. They're typically going to form diatomic gases. Now, if you look at chlorine, bromine, and iodine, they're a little bit different because chlorine will be a gas, bromine forms a liquid, and iodine's a solid. I2 is a solid at room temperature. Now, I don't want you to be thinking, okay, I've got to remember which one of these is which. I want you to remember these 7: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. I want you to remember those 7 as your diatoms or your diatomic substances. Now, when I was in high school, my chemistry teacher, Mrs. Jones, um, if iodine is solid, how does it become liquid when they sell it? That is a great question. And usually that iodine is in its ionic form. But I'd have to look at what, when you're selling it, what the actual form is. I think that it's like an iodic acid or it's like a very dilute acid or it's a potassium iodine. But I can get back to you on that. So Mrs. Jones, I remember she had this sign in her classroom and it had a picture of a person and this person looked like this. Had a mustache and then they had an open mouth and that was pretty much it. And they also had ears. It wasn't really like the art wasn't the point. Instead, the point was this person's name is H. Braun Cliff. It was a nice little mnemonic to remember H, hydrogen, Br, Br, O, O, N, N, Cl, Cl, I, iodine, F, fluorine. To remember all the diatoms. Now, I want to distinguish this and don't want you to think like, oh, well, what about, is there something like, what about P2? Two phosphorus atoms. Does that exist? And to put it simply, no, it's if you find phosphorus, phosphorus is not going to be bound to another phosphorus atom. Phosphorus is going to be bound to something else. All of these right here are unique because they're going to kind of prefer to form a bond with themselves to exist in kind of the natural world. Now, to visualize couple of these, we've got chlorine gas, bromine gas, and iodine gas. Chlorine gas is typically a kind of a yellow substance. You can see within each one of these flasks that there is like a visible component of them. You can see the color of these different gases. These other, like fluorine, oxygen, nitrogen, and hydrogen gas, you're not going to see a color to them. And that just has to do with their electronic state. Okay, so your takeaway from these first few slides is that behaviors of different elements, or there are Different elements have different behaviors. We've talked about the diatomic gases and the diatoms, H. Broncliffe. These are substances that they love to basically pair up with themselves. Now, as kind of a continuation of this, or where we go from this, I want you to remember we've seen this slide before, this picture before. And this is showing we've got two different solutions. Here's a clear solution in this, what is known as an Erlenmeyer flask. I'm going to label it as an E flask. And then we've got this kind of copper, like amberish solution in a grad cylinder. And if you look, the mass is 173.64 grams. That mass reflects, and I'll tell you that this volume is approximately 25 milliliters. This volume is about 25 milliliters. So if the density of these solutions is approximately 1 gram per milliliter, it's roughly 25 grams of each one of those solutions. So this mass right here is the solutions plus the glassware. And what we see happen is if you take all of the solution from your grad cylinder and add it to the Erlenmeyer flask, you'll see the volume go up. I'm sorry, this was, I guess I read that wrong. This is about 50 milliliters. About 50 milliliters. So we've got about 75 milliliters attributed to solutions, and then the rest of it's glassware. So we add our solution to here. Our total volume, I'll label it as TV, has not changed. Has the appearance of this changed? Absolutely, wholeheartedly. Looks considerably different. Now, the grad cylinder we left on there, and lo and behold, the mass remains the exact same. So the mass before our reaction and after our reaction is the same. This expresses and this shows our conservation of mass. Now, the identity of these two substances doesn't really matter for this. What I want you to recognize is that, well, all of the liquid between these two was conserved. So I'll say a liquid plus a liquid, you mix them together, and you get a liquid. And all of the mass is attributed to that liquid. Now, here we have a substance. This is identifying a specific compound. This compound is known as mercuric oxide. Mercury is Hg, and mercury has a charge of +2. Mercuric oxide is an ionic compound that is HgO. Okay. Now, is anyone looking at this, and you can set this as a private message, but is anyone looking at this and thinking, but wait a minute, you talked about oxygen being O2. Give me a Y or an N in the chat or a private message or whatever if you're like, wait a minute, shouldn't this be O2? If you took a pause and were like, I thought that should be O2. And you know what? For every person saying, yeah, I thought it should be O2, there's probably 5 other people who are like, I'm not going to add to the chat. Okay. Now, this does not have to be O2 because what do we have here? We have mercury as an ionic compound. Mercury is transferring electrons to oxygen. And whenever mercury transfers electrons to oxygen, what is oxygen able to do? I'll say this enables oxygen to reach its octet, to achieve a full octet. We got a private message. Isn't it because it's already bonded to something else? Perfect. Yes, absolutely. So I don't want you, what I was talking about with diatoms, whenever I talk about oxygen, think about oxygen is either going to be, and I would say this is a kind of good rule of thumb, is either going to be bound to another atom, and I'll say bound, even though it's a little bit tricky, um, bound to another atom slash get electrons from another atom. Or it will be in, or it will be paired with another oxygen atom. Okay. So could everyone give me a Z in the chat if this statement at the top of the screen right here helps clarify this HGO? If it doesn't help, give me an R in the chat. And you can send it as a private message if you prefer. Okay. And to and I think if you were to see this HGO and be like, wait a minute, you actually have the knowledge base that you've seen another compound that doesn't have, or sorry, has oxygen, but not as O2, H2O. That's one oxygen, but that's paired up with two hydrogen atoms. Okay, so what I'm getting at here is, and kind of where we're going with this is conservation of mass. We have this solid HGO, this mercuric oxide. And there's 100 grams of it. And if you were to get mercuric oxide and put it in a test tube like this, say that we got 100 grams of mercuric oxide into that test tube, and then you used let me go ahead and switch colors. I'm going to go to gold Bunsen burner. And all that you're doing here is you're adding heat to that solid. When you add heat to mercuric oxide, something happens. You're able to separate off 92.61 grams of mercury. That's a very unique and specific number. That's pure mercury. So this is Hg. That's a solid. Okay, so we started with HgO and we end with Hg. Okay, cool. Could anyone tell me, without looking ahead at the next slide, what is the other product here? Because spoiler alert, there's going to be another product. I'm going to give you a couple of options. A, B, oxygen gas. Love it. Great. Oxygen gas, which is O2. Could everyone give me a T in the chat if they are content with that? Or an O if, wait a minute, huh? How? Okay. So I saw a couple of O's in there. Basically, in this case, for this specific substance, when you heat it up, what happens is the mercury is going to kind of cluster together in some respects. Sure, I'll do my best to do that. Let's go with this one. I'll change to a different color. Maybe that will make it a little. Oh, that's better. Okay. So we've got HgO, and when you heat it up, we're going to separate these things off: solid mercury and O2. Could anyone tell me approximately the mass of O2 that remains? We started with 100 grams of HgO, and we separate off 92.61 grams of mercury. And I'll use my calculator. Very close. You're gonna end up with around 8, yeah, 7.39 grams of O2. Now that might be a little bit confusing. Gas has a mass? Can a gas have a mass? Absolutely. If you have a propane tank, think about propane if you're, grilling or something like that. If you sell propane and propane accessories, is that propane tank going to weigh the same when it's full versus empty? No, it's not going to weigh the same. When it's empty, it's going to be considerably lighter. What's the difference between a full propane tank and an empty propane tank? Well, the lack of the propane gas. So in this case, we've got mercury oxide and we heat it up. What happens is that solid mercury separates and O2 is evolved. Now, that might strike you as a little bit odd because, wait a minute, Hg, yeah, okay, so I see where the Hg comes in, but this is only one O. How's it O2? Well, what happens or what we're looking at here is a unbalanced chemical reaction. Now, in this case, matter is neither created nor destroyed during chemical change. Mercury oxide, you add heat, you separate mercury, you lose oxygen, and at the end of the day, you have a total mass of 100 grams at the start and at the end. Now, in this case, if you were actually doing this, well, unless you captured the gas, you'd lose all that O2. Now, in this example, this is something that I'm guessing that some of y'all have done before. You've gotten vinegar, you've gotten baking soda, you made a nice little volcano. NaHCO3 is, or sorry, that is your baking soda, NaHCO3. And then vinegar is CH3COOH. If you mix these two together, you're going to get CO2, H2O, plus a little bit of Na ions. Now, this CO2 gas, it's going to evaporate, or it's going to the gas is going to be produced, and if it's not captured, it's going to be lost. Now, if you do the same thing right here, the mass, let's say you put 30 grams of baking soda and 30 grams of vinegar, what is going to be the mass of the gas here and the liquid here? So I'll say liquid plus gas mass that is contained in this system right here. Can you tell me approximately the mass of all of that? Don't worry about the glassware. Just think about the masses of the combined liquid and gas. We started with 30 grams of vinegar and 30 grams of baking soda. 60. Perfect. Okay. So this principle or this idea that mass is going to be conserved is very important because that's at the heart of balancing a chemical reaction. Now, to look at a chemical reaction, something like this, I like to look at a chemical reaction or chemical equation and look at the individual molecules. Water, H2O, can be broken down into H2O and O2. Now, if you look at this and you say, okay, well, that, or if you look at that, that is known as electrolysis of water. So if you send an electric current through water, you're going to be able to produce H2 gas and O2 gas. Now, I'm guessing some of y'all are looking at this and saying, okay, well, I see my H2O, my single H2O molecule, and then I see my products, my H2 and my O2 molecules. And one thing that stands out is this is not balanced. Could everyone give me a Z in the chat if they agree that that is not balanced? Okay. You're absolutely right, it is not balanced. One of the issues is, well, you've got one, two hydrogen atoms, but then you've got one oxygen atom, and somehow on the other side you end up with two oxygen atoms. Well, how's that happening? In order for that to happen, you have to recognize that this solution right here is not just, so not simply one H2O molecule. Could everyone give me a J in the chat if they agree and understand that if you have a beaker filled with water, it's not just one H2O molecule? It's going to be more. I mean, it's at least two, at least four. It can be millions upon billions of water molecules. So don't stress about, oh, but do we have enough at this point in time? Think, okay, it's not balanced, but we've got an excess of it here. We are going to conserve mass. How are we going to do that? How are we going to conserve mass within this reaction? How are we going to have enough reactants to make enough products? Well, we've got to have two reactants, two H2O molecules, in order to make our two products. Now, if you look at this, when we added our second H2O molecule, so we just added the second H2O molecule, what that does for our O2 is it checks it off. It's good. We're good there. But when we added our second water molecule, what did we add? We added two more hydrogens, so we added another H2 molecule. Now, in order to kind of communicate this or express this, what we do whenever we're balancing a chemical reaction, balancing this right here, give me a P in the chat if you think the solution is to do this. Change it from H2O to H4O2. And give me a M in the chat if no, that can't be right. Okay, great. So H4O2, I'm going to say, is not the same as 2H2O. Can you give me a W in the chat if this idea makes sense to you? Okay. If you understand that, then you understand what it takes to balance a chemical reaction. Now, this number right here, oh, that was a bad highlighting selection. That 2 is known as a coefficient. So when it comes to balancing a chemical reaction, you love coefficients. You can play around with coefficients. This number right here, these 4s and these 2s, I'm going to go with blue. These are known as subscripts. Subscripts cannot change. You cannot change your subscripts because when you change a subscript, you change the molecule. Can you give me a U in the chat if you understand that if you change the subscript, you're changing the molecule? And then a S in the chat if, wait, you can't? Okay, great. Seeing lots of U's. So I think that it's really important to understand this right here, this at the bottom of the screen. Visualize a chemical reaction and think about what those molecules look like. Do we have a tool that we can use to visualize a molecule, to draw a molecule out? We do. We have our Lewis structures. So if you're ever confronted with a chemical reaction to balance, it might be helpful to say, okay, can I visualize that single molecule? And if you can, then write it out and draw it out, the reactants, and write out and draw out the products. Now, as we get more and more into balancing chemical reactions, you'll get to a point where you're like, I don't need to draw that out because I understand the principle that I can change my coefficients and communicate this, and I don't have to change my subscripts. Now, our mass is conserved there. And so this is really expressing, hey, we can change our coefficients to communicate this. So we have a balanced chemical reaction where we have two H2O molecules reacting, or kind of with an electric current sent through them to produce two molecules of H2 and one molecule of O2. Now, could everyone give me a 6 in the chat if, hey, that makes sense? Okay, great. Now, balancing a chemical reaction can be a little bit more involved. There are some instances where you get a chemical reaction like this. C plus O2. This is pure carbon. This would be something like graphite. Is going to react with O2 to produce CO, or carbon monoxide. This is not a balanced chemical reaction. So visualizing, giving yourself a tool, and maybe something as simple as like, okay, well, these beans, these black beans, are representative of my carbons. And I'm going to express this balanced chemical reaction by showing my two carbon atoms reacting with my two red beans that are kind of next to each other to express my O2 will give me CO and CO. So a 2 coefficient in front of carbon plus O2 yields 2 coefficient in front of CO. That is a balanced chemical reaction. Now, whenever you have low coefficients, it might seem like, oh, that's pretty simple and straightforward. But as the coefficients begin to grow, it might be a little bit more complicated. So this tool right here is linked. And I think that it's a helpful tool to use, but I think that it's also just good to be able to draw this out. So if you have 0 N2, 0 H2, you will produce 0 NH3. This coefficient right here says we have no N2, no H2, no NH3. Now, if we were to adjust this and say we've got N2, I'm going to change that to a 1. And then we were to adjust this right here. If we have one N2 and one H2, let me ask you this. These coefficients are important. Give me a Y or N. Do we have enough nitrogen in our reactants to produce NH3? Just the nitrogen. Do we have enough nitrogen, Y or N? Do we have enough nitrogen? There's 2 nitrogens as reactants. How many nitrogens do we need for our product? 1. Yeah, we've got enough nitrogen. We're good there. Okay. Now, the next question. The next question is, don't worry about it. And let's look at it from a different angle. To make one molecule of NH3, we need 3 hydrogens. Do we have enough H2, or do we have enough hydrogens in H2 to make our product of NH3? No, we don't. So our coefficients here, and some people, when it comes to balancing chemical reactions, they use this sort of guess and check method where they look at the coefficients and they say, okay, well, 1 do it. No, it won't. 1 is not enough. Okay, so what if I changed my coefficient in front of H2 to 2? Now my question is, will I have enough? Let's go back to the first question. Do I have enough nitrogen? Yes, I do. I still do. Do I have enough hydrogen? Yes, I do. So if I had 1 N2 and 2 H2, I'd be able to produce NH3. But then I've also got 1 hydrogen left over. And that hydrogen's all alone. And we know hydrogen doesn't like that. So I'm going to say left, I'll say left over. So that means that, is this balanced? No. I need three H2. Ooh, interesting idea. Okay, so Maya's saying that I need three H2. I think I like that idea. So I'm going to put a 3 in front of here. So I'm going to put H2, H2. Now I'm going to erase what I've drawn over here as my products. And I'm about to sneeze, but now that I've mentioned it, I'm probably not going to. Yep, I'm not going to. I avoided it. Um, I've got three H2s. Will that give me enough to make NH3? It will. Okay, so if it's helpful for me, like I said, about drawing the Lewis structures. I'm going to translate all of these to H, 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 H. Okay, so I used H3, so I'm going to highlight each one as I use them. One, two, and three. And then I'm going to go back to, I'm going to do N, triple bond N. I've used one nitrogen. And so now I've got, let's see, another nitrogen. And then H, H, H. Oh, I highlight that. Two NH3s. I'm going to go ahead and just for the sake of clarity, I'm going to scribble that out. Is my chemical reaction balanced when I've got one N2, three H2, and it's not zero NH3 because I made NH3. So I'm going to bump that to 2. And what you guys just saw was whenever I was in 8th grade, I got lots of B's and C's on my report card, and it was printed like this. And then I remember one time I was like, you know what I'm gonna do? I'm gonna use an eraser and I'm gonna make that an A. And my mom immediately saw straight through that. She was like, that's not an A. I was like, but it could be. Um, and then I was grounded for two reasons, the grade and for lying. So anyway, so yeah, what I was bringing that up was because I had a 0 there and I made that a part of my number 2. So does everyone agree that this is balanced at one coefficients of 1 plus 3 yields, and that arrow right there means yields or produces 2NH3. Can everyone give me a wired N on the chat if they're good with that? Okay, wonderful. So I think that a good strategy, especially when we're starting out, is to take our molecules, all of them, draw them out, and then do things like, okay, well, to make this, what do I need? And this is kind of where you can suspend what you know to be true and say, okay, well, I need a nitrogen. What are the building blocks for this? I need a nitrogen and I need 3 hydrogens. How am I going to get 3 hydrogens? Well, I can't do it with 1.5 H2 molecules, but I can do it with 2 H2 molecules. Okay, well, then I have excess. So now let's go on to a little bit more complicated. We're going to do this, and then that's going to be the end of it for the day. We got NaN3. Well, good job, Joel. You drew right over one of the important parts. NaN3. Okay, so the first thing is to go atom by atom, or I think that it's helpful to go atom by atom. Sodium, sodium, balanced. All right, great job, Joel. And you know what I'm going to do? I'm actually going to go to this right here, and I'm going to give myself a little coefficient space. I'm going to do the same down here. Coefficient space is good there. Then I'm gonna move my hint up here. Okay, so got my coefficient space. So that's where I'm gonna be putting numbers. Now, sodium's good, so I don't need to do anything with that. But N3, okay, that's where maybe I'm gonna have to begin adjusting it. And if I see 3 and I see 2, Well, 3 and 2 aren't the same. So then I've got the option. I can throw a coefficient in front of here. And I could go through the deliberate process of putting a 2 here. But what do I know that I'm going to have to do? If I have 2, what does that mean for the number of nitrogens on my product side? Well, if I got 2 out there, that means I've got 4. Private message, but they have the common denominator of 6. Spot on. That's exactly what you're going to do. You're going to look for a common denominator between these two numbers, 3 and 2. And what you're going to see is, well, if I put a 3 in front of this, that gets me 6 nitrogens on my product side. Then if I put a 2 in front of this, it gets me 6 nitrogens on my reactant side. Could everyone say J in the chat if they are good with that and they follow that, or a W in the chat if, wait. Okay, great. We kind of accelerated the process. And whenever we play around with, this is why I refer to it as the guess and check method. When we add a coefficient, we want to then check, are we balanced? And the answer to that question is no. Our nitrogens are balanced, but we put a 2 in front of the sodium. So how many sodium do we have on our reactant side? Dose. How many do we have on our product side? 1. So what do we need to do? Put a 2 in front of it. Now, just between the 86 of us, actually, I don't know if I am counted as a participant. Just between the 85 of us, I always feel a sense of accomplishment whenever I balance a chemical reaction. At this point in time, is this balanced? 2 sodium, 6 nitrogen, because the 2 applies to that. So 2, 2Na, 6N. 2Na, 6N. So we are balanced now. Okay, now we've got something that's a little bit more involved and a little bit more complicated. A recommendation is that you can start with oxygen. That's where we're going to start. We're going to start there because if we look at the oxygen on our reactant side, and remember, when we talk about oxygen here, we're talking about the element or the atom oxygen. We have 3 oxygen atoms. We're not talking about O2. We're talking about oxygen and then looking at the subscript. We've got 3 oxygens on our reactant side, and we got 2 oxygens on our product side. Well, it's worth your time to just go ahead and say, well, hey, we've got a common denominator. We know that we need to have an equal number of oxygens. So even though I put this 2, or I'll put this 2 in front of Fe2O3, that's going to get me to 6 oxygens. It's also going to tweak my number of irons, but I'm not too stressed about that right now. I've got 6 oxygens, then I put a 3 in front of here. That's going to get me 6 oxygens. So I'm good on my oxygens. Could everyone give me a Q in the chat if they understand that? And we haven't looked at the consequences, but we're going to come back to that. Okay. Now, the next step is to look at some of those consequences. Well, which elements were impacted? Which non-oxygen elements were impacted by this coefficient? Iron was impacted. Carbon was impacted. Ooh, carbon is a reactant where we have to account for that number. Then iron is a reactant. Huh. Let's go ahead and take stock. We've got Fe on the reactant side. I'm going to keep a running total of iron, oxygen, and carbon on the reactant side. I'm going to separate these two. And then iron, oxygen, and carbon on the product side. I've got 6 oxygens. I'm going to highlight those and say balanced. I am good there. What about my irons? Well, on my reactant side, I've got 4. And then I've got 1 on my product side. Maya, you are absolutely right. We throw a 4 coefficient in front of there. Multiply that by 4 and we get there. Now, carbons. Well, carbon, we've got more on the product side than we do on the reactant side. Is that a problem? No. All that we have to do, carbon is by itself. We're going to put a 3 in front of that. And we're good. Are we balanced? Well, down here are my totals. I've got 6 oxygens, 6 oxygens. Got 4 irons, 4 irons. 3 carbons, 3 carbons. Am I done? Give me a wire in the chat. Yeah. Does anyone else give me a 1 if yes and a 9 if I do not care? 1 if you have that sense of accomplishment or the feeling of accomplishment. Awesome. This isn't trivial. And to me, this is great because it's a process. You make a change, you see an output, and then you have to go back to that output and make a change. It's kind of like this volleying back and forth of like, okay, I made a change. Now I see an output. Now I have to reassess. Was that change, did it get me where I wanted to go? Not quite, but it's moving me in that direction. Okay, that's what I've got for today. I'm going to go ahead and stop my recording. I'm going to say, I hope you guys have a great Monday. And I'm going to be okay. Oh yeah, we got a private message question about a Michael Jackson song. Remember on Wednesday, if you need to join, absolutely. Um, but you're not required to. The exam's going to be through Proctorio. If you got any questions, I got office hours at 12:30. I do have a sick kid at home, so if I'm late or something, please just hang on. I'll be right back. But have a great Monday, y'all.